Imagine you're holding a pair of magical dice. You roll one in New York and someone else rolls the other in Tokyo. No matter how far apart you are, the two dice always show results that are perfectly correlated. Roll a 6 here and the other dice, thousands of miles away, will instantly roll the same number. No waiting, no delay. This isn't just a fantastical idea, it's the crux of quantum entanglement, one of the most perplexing and exciting phenomena in modern physics. Entanglement has not only been proven real, but is also fueling breakthroughs in technology, science, and our understanding of the universe itself. Because we'll unravel this mind-bending concept and explore why entanglement is more than just a curiosity, it's a key to the future. Chapter 1. Setting the stage, the quantum revolution. To understand entanglement, let's first step into the world of quantum mechanics, where particles defy logic and intuition. At its heart, quantum mechanics describes how particles like electrons and photons behave. Unlike the predictable, clockwork-like behavior of the classical world, think planets orbiting the sun, the quantum realm is governed by probabilities. Here's the kicker. A particle doesn't exist in a single state, but rather in a superposition of many states at once. An electron, for example, can spin both up and down simultaneously until measured. This bizarre behavior is beautifully encapsulated in the wave-particle duality, where particles can act like waves, spreading out and interfering with themselves. But the strangest revelation of all came when physicists realized that particles can become entangled. Chapter 2. What is quantum entanglement? Entanglement occurs when two or more particles interact in such a way that their quantum states become inextricably linked. From that point forward, no matter how far apart they are, the state of one particle will always correlate with the state of the other. Here's an analogy. Imagine a pair of identical twins. If you see one twin wearing a red hat, you'd immediately know the other twin must be wearing the same, even if they're on opposite sides of the globe. In the quantum world, this correlation happens instantly, faster than the speed of light. Physicist John Bell famously showed through his theorem that these correlations cannot be explained by classical physics or any hidden variables. The universe, it turns out, behaves in a way that is fundamentally non-local, defying our conventional notions of cause and effect. Chapter 3. Schrödinger's cat and beyond. To truly appreciate entanglement, we need to revisit one of quantum mechanics' most famous thought experiments, Schrödinger's cat. Erwin Schrödinger devised this paradox in 1935 to illustrate the absurdity of quantum superposition. In his experiment, a cat is placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers the release of the poison, killing the cat. If the atom doesn't decay, the cat lives. Quantum mechanics tells us that until we open the box, the cat is both alive and dead, a superposition of states. Now imagine linking two such boxes together. The moment you open one box and find the cat alive, the other box must contain a dead cat. This instant knowledge transfer mirrors the behavior of entangled particles. It's as if the universe itself is deciding the outcome of both measurements simultaneously. Chapter 4. Einstein and the EPR paradox. Not everyone embraced entanglement with open arms. Albert Einstein, a towering figure in physics, famously derided it as spooky action at a distance. Along with Boris Podolsky and Nathan Rosen, he proposed the EPR paradox, arguing that quantum mechanics must be incomplete. Einstein's discomfort stemmed from his belief that no information or influence could travel faster than the speed of light. Entanglement, however, seemed to violate this principle. If measuring one particle instantly determined the state of another, it implied a form of faster-than-light communication, or at least a mechanism we couldn't yet understand. For decades, physicists debated whether entanglement was real or simply a mathematical quirk of quantum theory. Chapter 5. Bell's theorem and experimental proof. In 1964, John Bell devised a brilliant way to test whether entanglement could be explained by hidden variables. His theorem demonstrated that if quantum mechanics were correct, measurements on entangled particles would violate certain mathematical inequalities, known as Bell inequalities. Experimental tests of Bell's theorem, conducted over the following decades, consistently showed violations of these inequalities. This provided overwhelming evidence that entanglement is a real phenomenon, not explainable by classical physics or hidden variables. In 2015, loophole-free experiments sealed the deal. Physicists entangled photons and measured their states with unprecedented precision, conclusively ruling out alternative explanations. Chapter 6. Applications of quantum entanglement. Entanglement isn't just an academic curiosity, it's paving the way for transformative technologies. Let's explore some of the most exciting applications. Quantum computing. Traditional computers process information in binary bits, zeros and ones. Quantum computers, however, use qubits, which can exist in superpositions of 0 and 1. When qubits are entangled, their computational power grows exponentially. This enables quantum computers to tackle problems like simulating complex molecules or optimizing massive data sets that are impossible for classical machines. Quantum cryptography. In an era of growing cyber threats, quantum cryptography offers unparalleled security. Entanglement-based protocols like the BB84 protocol use the principles of quantum mechanics to create encryption keys. Any attempt to intercept these keys disturbs the quantum state, instantly revealing the intrusion. Quantum networks. Quantum entanglement enables the development of ultra-secure communication networks. Scientists have already achieved quantum teleportation, transmitting quantum states over hundreds of kilometers. In the future, quantum internet could revolutionize how we share information, making it faster and more secure than ever. Quantum sensors. Entangled particles are incredibly sensitive to environmental changes. This makes them ideal for developing next-generation sensors capable of detecting gravitational waves, monitoring brain activity, or even mapping underground structures with unprecedented accuracy. Chapter 7. Philosophical implications of entanglement. Beyond its technological impact, quantum entanglement raises profound questions about the nature of reality. Is reality local or non-local? In classical physics, events are local. They happen in specific places, influenced by their immediate surroundings. Entanglement, however, suggests a fundamentally non-local universe, where distant events are mysteriously connected. What is the nature of time and space? If entangled particles can affect each other instantaneously, what does this say about time and space? Some physicists speculate that entanglement hints at a deeper, hidden layer of reality, where time and space as we know them don't exist. The unity of the universe. Entanglement challenges the notion of separateness. It suggests that at a fundamental level, all particles, and perhaps all things, are interconnected. This idea resonates with philosophical and spiritual traditions that emphasize unity and interconnectedness. Chapter 8. Challenges and future directions. While entanglement has opened new frontiers, it also presents challenges. Scaling up quantum systems, reducing decoherence, the loss of quantum states due to environmental interactions, and integrating quantum technologies into existing infrastructure are significant hurdles. However, advances in materials science, engineering, and computational algorithms are rapidly overcoming these barriers. The next decade promises exciting developments, from quantum computers solving real-world problems to the deployment of global quantum communication networks. Conclusion: the quantum age. Quantum entanglement is more than a scientific curiosity. It's a portal to a new understanding of the universe. As researchers continue to push the boundaries of what's possible, Entanglement will undoubtedly play a central role in shaping the technologies of tomorrow and the philosophical debates of the future. By learning about entanglement, you're not just exploring a fascinating phenomenon, you're engaging with the very fabric of reality. Welcome to the quantum age. Subscribe and hit that like button for more amazing facts.